joke. Yeah. You were just supposed to like him. You weren't supposed to like actually watch him. The what? Oh, I didn't even see that. That's where the girl ran. She just stopped. So I don't know if you saw it. I don't know if it was a different play, but I was guarding her like on defense, and she just stopped in the middle of the field, and I ran into her and like sprained my finger. Oh, was that good? Oh my gosh. It's all a big blur. Okay. Well, so there was this scavenger hunt. Could you flip that first slide off, please? Oh, yeah. So it was a scavenger hunt, 24 hours. They had 200 various things that we could do all over the state. Even you could go to the Pacific Ocean if you wanted to. That wasn't worth enough points for us. But so we just did as many of these stupid, silly, crazy things as we could in 24 hours. And then there were like 130 teams or something, and we got 8th place, which means that we have a chance to win, and the winning team goes to Belize to compete. So, but the way that it works is now it's all the peer voting. That's why I emailed you guys. So the more likes you get, the better your score. So even though the first place team crushed us with total points, we could still beat them with the peer voting. So thank you if you participated, and during class I will let you know how you will redeem your extra credit. But yeah, I suppose there's some entertaining things on there in terms of me doing the stupidest things ever. Okay, so was it fun to watch? What was your favorite? All right, so this one. So what the whole point is with these is we know we can write a series like this, a times r to the n, as a over 1 minus r. So if we have a function that looks like this, if we can get a function that looks like this, then we can go backwards and write it as a series. So functions that look like this, we're able to write kind of in an infinite polynomial form. Okay, that's what we're doing here. So we're given this. How do we get it to look like that? So what do we do to that to get it to look like that? Take the derivative. Okay, so the derivative is 1 over 5 minus x times negative 1. Or negative. All right, so there's one big problem with that, though. It does not look like this for what reason? The 5. You've got to have a 1 there. It has to be a 1. We talked about that last time. So I need to adjust this, change the form of this so it doesn't change its value, but there's a 1 there. So basically, it's kind of like you can think about this as dividing the top and bottom by 5 or factoring 5 out of the bottom. Both ways work. So I'll factor a 5 out of the bottom. So that would mean negative 1 over 5 times 1 minus. So 5 times what is x? X over 5 or 1/5 x, yeah. Right. So this now is the same as negative 1/5 over 1 minus 1/5 x. And that now is this form a over 1 minus r, so we can write it as series. And so the series would be negative 1/5, 1/5 x to the n. Okay, and so then I recommend that you write that both ways. So this is what? This is our f prime, and it's equal to that thing. And let's write out, and I recommend that you write out the terms, because if you get the terms right, then derivatives and antiderivatives of polynomials are kind of like we can fall back on that. We know that that's right for sure. things get a little dicey when we're doing antiderivatives and derivatives of expressions like this. We're less confident, right? So get the terms and use that as your checkpoint. Okay, so when n equals 0, we have -1/5. N equals 1 is at -1/25 x. N equals 2. How's that looking? Agree with that? And then what do we want? So this is, if this is f prime, then we want now antiderivative of that. So antiderivative will be f. Okay, but so now this one, there's actually a little catch to it, okay? There's a little catch to this. When you have a rate function and you find the amount function, so like for instance, if you do the integral of x squared dx, rate of change is x squared. So the amount function is x cubed over 3, right? But is that the only amount function that has that rate function? Yeah, any vertical shift of an amount function has the same rate function. Just moving the function up and down maintains the rate profile, right? That's why you add plus c to the amount function given a rate function, because there's an infinite number of amount functions that have that rate of change, right? Remember we said x squared is a rate of change function. So you can add any constant to a function and it'll maintain the rate of change. So we have to keep that in mind on this one, okay? So actually, so when we do that rate of change, or so that antiderivative, we have to accommodate for a constant. So let's put that in here, c plus. So antiderivative is keep the -1/5, and then it's going to be 1/5 x to the n plus 1 over n plus 1 but then, so if we imagine taking the derivative of this, we'd also have a times 1/5, right? So then to get rid of that, we need to multiply by 5. So we're doing antiderivative. Remember the antiderivative, we think about taking the derivative as a check. So I raise the power divided by n plus 1, and I think, okay, if I took the derivative of that, it would be times 1/5. That I was just focusing on this that I don't have. So then it needs multiplied by 5. Yeah. So that's just the power rule, right? So I'm going to raise the power. So just like I did here, right? I raised. You see how I got the 3 down here? It's the same thing. Yeah.
Why don't you set n equal to 1?
Why don't I set n equal to, starting with n equals 1? That was when we took the derivative. That was in the situation where we took the derivative. But I'm taking the antiderivative.
Why is that?
What's that?
Why is that? Why do you do it?
Yeah, nothing I can explain quickly and easily. But I appreciate the question. But we could sit down and kind of talk about it. But for time's sake, we'll just go with it. But again, that's why we do these terms over here. Like if you're ever not sure, do these terms over here and then make sure it agrees with whatever index you started with. Okay, so this simplifies then that you got the 5 here and the 1/5 here go away. So then you just have this. Okay, now we're going to write out the terms. We're going to do the antiderivative of each term, right? So it's going to be antiderivative of this is going to be c. We're going to have a c plus, or we might -1/5 x minus x squared is at 1/50th, or let's do 1/25 2 times 5 squared x squared minus x cubed over 3 times 5 cubed minus x to the 4th over 4 times 5 to the 4th. Okay, agreeing with that? So now, I did the straight antiderivative of these terms. I did the antiderivative of the summation form, so that this should give me these exact same terms. Like this is our way over here of checking this. So when n equals 0, I get negative 1/5 x. Correct. When n equals 1, I'm going to get negative, so it's going to be negative 1/5, all that squared over 2. Yep, that whole thing squared over 2. When n equals 2, we get that whole thing cubed, x over 5 cubed over 3, negative. Yep, x over 5 cubed over 3, negative. So it's working. Okay, it's working. So then, how do we know what the constant is? So basically, we know what the constant is by looking at f of 0. So this is our function that we wanted. So this should be the same as ln of 5 minus x. So so we're now solving for this constant. What is f of 0? Truly, what is f of 0 based on this? Ln of 5 minus 0 or ln of 5. So without the constant, what is the f of 0 of what I found? See, so this is supposedly the same function as what we started with, right, in polynomial form. What's f of 0 of that? What I found? That would just be 0, right? So, but we don't want it to be 0. We want it to be, if you plug in 0, we need it to be natural log of 5. So that determines what the constant is. So that constant is ln of 5. So it's going to be ln of 5 plus all those terms, then gives me the actual function. Because if I leave that constant off, I plug 0 into that function, I get 0. But if I plug 0 into the original function, I get ln of 5. So that we got it. So we need that constant so that when we plug 0 in, we get the ln of 5. And so again, that's the vertical. So because why? Because we took the antiderivative. So this is like the rate function, and it's like the amount function. So which amount function do we have? We have the one that will give ln of 5 when x equals 0. So that determines that constant. All the other ones that we saw, f of 0 was 0, so you didn't have to worry about that, right? If you plugged in 0, you got 0. So but this one, you have to watch out for the fact that at 0, you don't get 0. You get ln of 5, and so they have to adjust for that. Questions on this one? Please.
So how come the 0 terms like match up, but like the 1 terms don't?
What do you mean?
If you did like f of 1, like that opposite is equal to 1 over 5.
It will if you have all infinitely many terms,
Oh.
right? So this is only the first 5 terms of the series, but it's an infinite series. Does that make sense?
Yeah.
So if you had all infinitely many terms and you plugged 1, then the limit of that sum will be whatever. No, it's got to be in the radius. It's got to be within. First of all, it's got to be within the. What's the radius of convergence end up to be for this one? Will it be 5? All right. So if it's 5, then it should converge on 1 because it'll be. Does that make sense though? This is only an approximation because it's not all the terms. It's an infinite series. So to get f of 1 to be the same as f of 1 up there, you need to keep adding and adding and adding, and then your limit of that sum will be f of 1. Does it make sense? It doesn't look like light bulbs are going off. The whole purpose of these infinite series is to make it, for it to be equal, for it to converge, you need all the terms. So if you cut it off short, then it's not going to be the same because it's not the whole thing. This is an infinite polynomial, right? I mean, you keep adding terms. It keeps going and going and going. It only converges as you keep adding more and more terms. Other questions?
If f of, when you plug in, if you have another function and f of 0 is not 0, should we plan on just making sure we add in c to add any constant into our?
Yeah, so this will happen when you take antiderivative, right? Antiderivatives, you've got rate and you're doing amount, and you got to think I've got all these different possible amount functions. So yeah, that's when you're going to have it. That's where you're going to have it when you are doing antiderivative to get your answer. Just watch out. If it's f of 0 is anything but 0, then yes, you need the constant. Yeah. Other questions? Yeah.
So f of 0 is anything besides 0. Does the constant take the place of f of 0, or is it 10 before?
If there's no, okay, so if this happens to, will it result? I guess it won't. It will never result in a constant. Thinking the antiderivative will always end up with terms that have all x's in them, right? So then it seems like that constant should be f of 0 of the original, but just always check. I don't want to say that. I don't want to say that definitively, but taking the antiderivative means that you're always going to have x's in those terms, so all those are going to go away when x is 0, leaving the constant to be f of 0. So that seems correct. Yeah.
So that's what they do when they say non-zero, like find the non-zero.
Yeah, but if they say yes, the non-zero terms, yeah, will be.
That's what they're referring to. Sometimes it's C, like disregarding C.
Well, if they want the first such and such non-zero terms of this series, you have that's non-zero. That's going to be one of them. Yeah. But all it means is don't start by putting 0 in because you worked it through and you have 0 here. Don't put a 0 in the answer. That's all they're saying. Start with the first non-zero term. Yeah. Other questions? Okay, let's do the next one. We'll move on. Okay, arctan x squared. So again, we're looking for something like a over 1 minus r. How are we going to get that from arctan of x squared? Again, derivative, right? Again, derivative. I don't have room. Move it over. Let's see here. All right, so we're going to do derivatives. So if our f of x is arctangent x squared, then derivative is 1 over 1 plus x squared times 2x by the chain rule. So what do we got? This one is all ready to go. We got the 1, so a equals, you can do 2x, r equals negative x squared, okay? So our f prime is going to be 2x times negative x squared to the n. Writing out the terms, n equals 0, we get, is that 2x? N equals 1, that's going to be negative 2x cubed. Okay, be careful here. So n equals 2, that's going to be x to the 4th. So this would be plus 2x to the 5th. Am I doing this right? X equals 3. Negative x squared cubed is going to be to the 7th, so negative 2x to the 7th, etc. Okay, taking the, so now if that's the derivative, yeah, please.
Should it be 1 over 1 plus x squared squared? So it's x squared. Derivative of arctangent is 1 over 1 plus x squared, but your x is x squared.
I'm
You pull the x squared out.
not following the question.
So when you take the derivative of arctangent, it's 1 plus x squared. But in this case, the x is within arctangent is x squared. So we
Right.
just square that. This is x of
So you use the same rule, take the x squared out, 1 over 1 x plus x.
Oh, he's right. He's right. Yeah, it's 1 over that thing squared. He's absolutely right. And that's, okay, that was the mistake that we made in office hours too. So, thank you for saving me from writing a lot of wrong stuff. Yeah, it's, so, yes, 1 over, it's kind of tricky because the formula is 1 plus x squared, so it's easy to miss that. So 1 plus x squared squared times 2x. All right, so therefore, r is minus x to the 4th. Very good. Okay, so minus 2x, so 2x to the 5th. Is that right? 2x to the 9th. 13th. Yes, please.
Is your top term not now 4x?
No, it's still times the derivative of the plugged-in function. This is just the formula for arctangent, so that doesn't play into the chain rule. So I think we got it now. Is this right now? Okay, good. Thank you. And so then antiderivative is what? Antiderivative is going to be f. And so we'll just write it in there and check it later. So c plus, just to get in the habit. Antiderivative, so it's going to be that thing to the n plus 1. Over n plus 1 times no, we have to write this. We got to write this all as one x term. If we're, yeah, we got to write this as 2 times x times negative x to the 4n which is negative 2 times x to the 4n plus 1. So but the negative is inside the n. Oof, jeez.
I said negative 1 to the n x 4n plus 2.
No, we're doing antiderivative. We got to get these x's together. So the negative comes after the x to the 4th, but before the n. Thank you. That's how you do it. So negative 1 to the n times 2 times x to the 4n plus 1. That's right. Okay, so here we go. Now we're ready for antiderivative, which is negative 1 to the n, c plus negative 1 to the n times 2 times x to the 4n plus 2 over 4n plus 2. We made it. Teamwork. Okay. So now, let's do these terms one by one and make sure it equals this. Antiderivative. So c plus x squared plus minus x to the 6th over 6, so 1/3. X to the 10th over 10th, 1/5 x to the 10th. One more, x to the 14th. So it'll be minus 1/7. So when n equals 0, we get x squared 2x squared over 2, x squared. When n equals 1, we get negative 2x to the 6th over 6. Negative 2x to the 6 over 6, right? When n equals 2, we get positive 2 times x to the 10th over 10. 2x to the 10th over 10 is 1/5 x to the 10th. It's working. Questions? Oh, last one, yeah.
Is it possible to just pull the x squared up from the beginning and find the series for arctan
Mm-hmm.
and then multiply by x squared?
Yep. Yep, that's fine. So yeah, I ended up embedding it in there as a. That's right.
So like on the test, if we just have arctan memorize, we just go through multiply by x squared and then we find.
If it's right, it's right. Unless I specify you do it a certain way. But here I'm not.
So x squared is considered the 0th term?
The way this is yes, the way this is going right now. When you put n equals 0, you get x squared.
So then
So that's. Go ahead.
what would the c term be?
Well, now we got to see if we have a c, right? So what is when x is 0? What is this? So like if this is f, what is f of 0? It's 0. Arctan of 0 is 0. Okay. So therefore, if we plug 0 into this, we need it to be 0, which means we don't need a constant. See that?
If it exists like for the element of 5,
Mm-hmm.
would that be considered? It's not the end.
Yeah. If you plug 0 and you get something other than 0 here, then you're going to have a constant in here. Does that answer it?
No, it's not. So if x squared is your term when n equals 0,
Right.
what does n equal when c is there? You just.
Oh no, see, it's not part of this. It's not the constant is not part of your series.
Okay.
You see, it's out here. Yeah. You just do it separately. C plus the series. Yep. Okay, and so then they ask for the integral of arctan x squared dx, which maybe there's some technique, but now that we have it, it's equal to this, we can just do the integral of this, right? So this function is arctan x squared. So for this part b, we have a different form of this function, so we can use it, and it's easier because it's just polynomial, right? So, and it says the first 4 non-zero terms. So x squared minus 1/3 x to the 6th plus 1/5 x to the 10th minus 1/7 x to the 14th. So that is the first 4 non-zero terms of our series for arctan x squared. So that's what we do. So, and that's much easier than trying to figure out some technique to do arctangent of x squared. So here's one advantage to writing these things as a power series, because polynomials are just nice to work with, right? Polynomials are friendly when it comes to derivatives and antiderivatives. So it'd be just x cubed over 3, yada, yada, yada. So you're just doing easy power rule antiderivatives. Okay, questions on this one? Yeah.
For the approximations, how many terms do you go in the series?
However many you need.
So like part C, so like
They're saying use part B, so you're going to use all those terms.
Okay.
Yeah, so it says the first 4 non-zero terms. So using part B, you're going to use all those. Yeah, yeah. Question?
What is C? As in, I know it's the constant, but what is the constant for this?
Well, f of 0 is 0. Like you go back to the original function. You plug 0 into that, you get 0. So it's whatever you need. Your constant's whatever you need so that fact holds true. Because we're rewriting this as a different form. So what c do we need so that f of 0 is 0? 0, because when you plug 0 into all these terms are 0. So c is also 0. Okay, good questions. Any more? Yes, sir?
If I give you a series, it's an n plus 1, but I need a c and x to the n. Can I give you a series? It shows how to
A
do
different problem? Let's just do it after class or outside of class because we got to move on. Yeah.
So let's say this function did have a c term and it asked you the integral of arctan x squared.
Mm-hmm.
Would you have to integrate the c as well?
Absolutely, because that c is part of the function, right? F of x is c plus that series, and f of x is arctan. So if you're integrating arctan, then you got to have that c in there, and that's gonna play a role into the integral. Yeah.
How do you find the radius of convergence?
So they're all, you always find that from the ratio test, right, on your series. So this is a ratio test problem. So to get radius of convergence, you'll do ratio test. Is that like a hard one? Is that saying that's hard? You want me to do it, or?
It's just I couldn't get to a point where the ratio test was applicable. So I did it with the two.
Yeah, so you're going to do the ratio test on this. So we could do it outside of class if you want. Yeah.
So if c isn't 0 and this is right the first 4 non-zero terms, would you include c in the
Yes.
first 4? Or just
Yes,
the
because
x?
it's part of f. Yep. Because it's part of the function f. You got to have the c right. Yep, absolutely. Yeah.
Radius of convergence will be the same for the antiderivative one. Always?
I don't know about always.
Okay.
Is that how they were working out?
It looks like it.
Okay. I just hate. I don't know if it's always, so I don't want to say it's always. Maybe. Just do them both. Other questions? Okay, let's change gears or move forward the conversation. Last chance. Good. Here we go. So Taylor and Maclaurin series. Let's Okay, so this is a really narrow functions that can be made into a over 1 minus r, or by a derivative or antiderivative to get a over 1 minus r. It's a very narrow scope of all functions, right? So that's relatively few functions in the world, in the universe, can be made to use this technique that we just worked on. Okay, so it's a restrictive technique. It only works on a relatively few functions. So Taylor and Maclaurin series then allow for writing any function as an equivalent power series. Okay, so here is a Taylor series centered about x equals a is a power series of this form. Okay, and then n, that n there is fna is the nth derivative evaluated at a. So the nth derivative evaluated at a divided by n factorial times x minus a to the n. And we'll see what it means later for something to be centered at x equals a, but just kind of accept that for now. So now I want you to write out, right, what that means, right? So you see that, you think what, okay? So see that, think what? Important exercise here. And if we can't do this, then all the stuff we're working on is kind of pointless. This is the very definition of what a series means. So when you see that, you think what? Who can tell me? Yes, sir.
It's the sum of all the outputs of the series such that it's I can't think of what the words.
No, tell me mathematically. I'm not asking for a sentence. I'm asking for mathematically. What is it? So
X to the 0 of a divided by 0 factorial times x minus a to the 0 plus f to the first of a divided by 1 factorial.
Hold on. Okay, plus
F of a.
f,
So f of a.
first derivative,
Divided by 1 factorial times x minus a to the first power, and so on and so forth with increasing numbers.
then the second derivative,
Third derivative, etc., on forever.
on forever. How's he doing? Good. All of us should have been able to do that, okay? If you can't do that, then all these exercises that we're doing are meaningless, right? You have to have just a good concept of what, when you look at this summation notation, what is it you're looking at? Okay, so the 0th derivative is just the same thing as the function, okay? The 0th derivative is just the function, and then after that, when n equals 1, you got the first derivative, n equals 2, second derivative, etc. Okay, any questions on that? So now, a Maclaurin series is a specific Taylor series. It's the Taylor series centered about x equals 0. So this is for centered about any value a. And so in a Maclaurin series is specifically when you're centering at x equals 0. So now I want you to write both for Maclaurin. Okay? For Maclaurin series, I want you to write it in the series summation form and the meaning form. So Maclaurin is the specific Taylor series centered about x equals 0, where Taylor series is centered about any value a. So can you write both? Can you write Maclaurin series in summation form and in explicit form? Okay, how about someone on this side? Can you tell me what this will be here, the summation form for Maclaurin series? Yeah.
So A is going to be equal to 0, right?
That's right.
Okay, so I guess we just have x to the n over n factorial left.
Okay.
So it would be 1 plus x plus x squared over 2 factorial.
Okay, so what's happening here then, if we're centering about 0?
Then A is 0.
Mm-hmm.
So if you're multiplying a function times 0.
No, this is the input, right? This is function notation. This isn't multiplication.
Oh, okay.
Yeah, this is function notation,
So
right?
you'd have f to the 0 times, or f to the 0, and then the next one you have f prime is 0. Then.
Right.
So
Right. So yeah, so we're plugging 0 into all those derivatives, and then instead of x minus a to the n, we'll just simply have x to the n. So this is the Maclaurin series. So a is 0, so you have all the derivatives evaluated at 0, and then x just simply x to the n. So this is what you should have had for that. Okay. So this is easier, right? So the Maclaurin series is easier because it simplifies the form a little bit. So we'll start with that. So we're going to write the Maclaurin series for y equals e to the x. Okay, y equals e to the x. So to do that, what we need is all the derivatives, the function and all the derivatives of evaluated at 0. So so f of x, I should really put this. Okay. Okay, there we go. So all we need then is every derivative evaluated at 0. So we can just make a little table here, 0, 1, for different values of n. Okay, and then this is the 0. So now we're doing the 0th derivative of f. And our function f is e to the x. So that's just the function. That's just the function, e to the x. And now this is the function evaluated at 0. So what am I doing? I'm finding this term right here. The 0th derivative evaluated at 0. What is it? 1. Okay, now the n takes us to the second term, which is the first derivative. So the first derivative, we take the function, first derivative is still e to the x. And then we're going to evaluate that at 0. And we're finding this thing right here. What is it? 1. Second derivative, evaluated at 0. Third derivative. Can we stop now? Yeah, it's just going to be the function. Every derivative is e to the x. Evaluated at 0 is 1 for this particular function. So now we're ready to set it up. So all derivatives are e to the x, which equal 1 when x is 0. Thus the series is. So now these are the values that we need here. The function evaluated at 0, the first derivative evaluated at 0, the second derivative, third derivative, etc. Okay, so this last column is what we're going to use here. And when you plug those things in, remember that 0 factorial is 1. 0 factorial is 1. So you get 1 over 1 plus 1 over 1 times x plus 1 over 2 factorial x squared plus 1 over 3 factorial x cubed, etc. Now, if you do the ratio test on this, it converges for all x. Okay, if you do the ratio test. So this series then, if you take enough terms, will converge on the whole function e to the x from negative infinity to infinity. So let's just really fast take a look at that. So what is it? 1 plus x squared divided by 2 factorial. Let's do the first 4 terms and see what that looks like. So the original function's blue, and our approximation's red. Okay, so you see e to the x is the blue one, and you see the red one is trying to approximate it. And where is it doing really well approximating it? At 0. This is the idea of centered. So Maclaurin center is centered at 0, so that it starts at 0, and the more terms you add, the better it does further away from the center. Okay, so it's like perfect at the center, but then as you add more terms, it gets better and better away from the center. That's the idea of the center. So if I add on a bunch more here, so that copy fourth, four, fifth, and 5. Six, go up to 6. Okay, so notice where it's black, it's where it's like almost on top of it. And then the blue one is the actual one coming down here and being asymptotic, and the red one here about -2, -3 then peels off and stops and it's not good anymore. But the more terms that you add, the more that red function, the left side is going to approximate that asymptotic e to the x there at 0. But you see where it's all like black here? It's like really, really close. It's in the middle. And you see like here at around 4 now, it's starting to diverge, so like 4, 50. So here between -2 and 4-ish is really good. And then greater than 4 and less than -2, the red graph, our approximate Maclaurin series, is then peeling off of y equals e to the x. The more terms that you add, the better our red function will do at matching y equals e to the x. Okay? And so this is really cool because this works for any function. The Taylor-Maclaurin series works for any function, not just the ones that are like a over 1 minus r. Okay, and then what this allows us to do then also so then it's easy to, so now that we have this e to the x, we can do slight variations on this without having to go through the table. Like we don't have to start from scratch, for instance. First of all, we can like estimate e to the 4th. So how can we estimate e to the 4th? Well, we could use the Maclaurin expansion of it. So rather than, so we could plug in, so to do e to the 4th, you could do 1 plus, what, 4 plus 4 squared over 2 plus 4 cubed over 3, and you could get as close as you want by taking more and more terms. Okay, so e to the 4th is approximately equal to 1 plus, you're basically plugging in 4 for x, and you're using the Maclaurin series version to do it. And the more terms you add, the better approximation it will be to e to the 4th. Okay? Similarly, how could we find the series for e to the minus 3x? So we could start over for e to the minus 3x and find all the derivatives, and then find them all at 0, and then build it from scratch. Or we can just use e to the x. So if e to the x is this, then what's e to the minus 3x? So then therefore e to the minus 3x is equal to sum of, how would I set this up? So now it's e to the minus 3x, so it would be negative 3x to the n over n factorial. And that would equal 1 plus negative 3x plus negative 3x squared over 2 factorial, etc. So you can use a basic one like EX then to generate lots of similar ones that are just slight variation. You don't have to start. You could start from scratch and build the table and build it, but you could just use e to the x to do that also. So how would you do x squared times e to the x? What would you do to our series? So what would you do to this to find the series for e to the x times x squared? Just multiply by x squared, just like we did in the previous problem. So it would be what? X squared times that would be x to the n plus 2, right? Over n factorial. You'd have x to the n plus 2, and then everything would be multiplied by x squared. Okay, this one's kind of interesting. Look at this. E to the x minus 1 minus x. So can you see how you would do that? So if this thing is e to the x, right, looking at this is e to the x, then what would e to the x minus 1 minus x be? Can you see it? Yeah, so, yeah, exactly. So if this is e to the x, then e to the x minus 1 would be not what I wanted. Where am I? Wrong page. Let me do this here. Okay, so if that whole thing's e to the x, then what would e to the x minus 1 be? So here you're subtracting 1, subtracting x. You're not going to mess with this. You're going to look at this and say, oh, if it was minus 1, then that would be gone. Minus 1. I just subtracted 1 from it. And then this would be gone. I just subtracted x from it. And now e to the x minus 1 minus x would be the same series starting from x squared over 2 factorial on. Did you catch it? Make sense? Okay. Here we go. So your turn. Write the Maclaurin series for cosine 3x. Cosine 3x. So I recommend build the table. Okay? So building the table is about getting those values in this last column. This is what you need to build it. You need these values in the last column. All the function and all its derivatives evaluated at 0. But now f is cosine 3x. Okay, can I leave the screen? Do you have this task written down? So set up this task so I can leave the screen and get your attendance. Okay. So the zeroth derivative is just the function. So that's just going to be the function. Okay, evaluated at 0 is? Cosine of 0 is 1. First derivative, negative 3 sine of 3x. Evaluated at 0. Second derivative. Okay, so I'm going to write 9 as the opposite of 3 squared. Cosine of, evaluated at 0. Negative 9. Or, which is the opposite of 3 squared. Okay, third derivative. Positive 3 cubed sine of 3x. 0. Fourth derivative. 3 to the fourth cosine of 3x. Evaluated at 0. 3 to the fourth. And then keep cycling here. So now we're going to have minus 3 to the fifth sine of 3x. Evaluated at 0. Let's do one more. Because really the non-zero terms are what's going to build this series. So let's have at least 4 of those. So it's going to be, what, negative 3 to the 6th cosine of 3x. Evaluated at 0. The opposite of 3 to the 6th. Questions so far? So here we go. So this thing is equal to 1 over n factorial x to the n. No, x to the 1. What am I doing? N is 0. Hello. Start over. Oh. We're doing one n at a time here. So n equals 0 gives 1 over 1 times x to the 0 is 1. Is that right? I'm going to write it out. Too much to keep track of. I'm going to write it out first. And on and on and on. So once we see the pattern, we'll get it. All right, so this first one. Function of evaluated at 0 is 1 over 0. That's just going to be 1. This one's going to be 0. That's 0 right there. Okay? Second derivative evaluated at 0. Negative, I'm going to do 3 squared times x squared over 2 factorial. Okay, then we're going to have 0. And the next one we're going to have is 3 to the 4th, positive 3 to the 4th, x to the 4th over, then we're going to have a plus 0, then we're going to have a minus 3 to the 6th, x to the 6th over 6 factorial. So, okay, so that seems easy, but what if we wanted to write this in summation notation now? Can we work backwards looking at what we have? Can we form a formula that gets this? Okay, so look, so first of all, so now we're going to change n so that n just gives us the, what? Just gives us the non-zero terms. So this isn't going to be the same n as this, okay? It's going to be a different n. So we can still start from n equals 0, but this is going to be, let's do that in red. So now n is going to be, this is going to be 0. This is going to be n equals 1. This is going to be n equals 2. This is going to be n equals 3. So this is the trickier part. It's coming up with the formula for it. So it's easier to go out here and look at a larger term to figure out what we've got. So first of all, we have, it's alternating, right? Positive, negative, positive, negative. So let's do that first. So if we do negative 1 to the n, do we have the right signs in the right places? When n is 0, it should be positive. When n is 1, it should be negative. That works. That's good. Okay, so we took care of the alternating. So now we come out here and we say, okay, so it's always going to be 3. We got 3 to the what? So when n equals 1, it's 2. When n equals 2, it's 4. When n equals 3, it's 6. So 3 to the 2n. And then we have x to the, also to the 2n. All over. Quantity, it's always twice, so 2n factorial. So now we just got rid of the zero terms, right? We changed it so that n equals 0, 1, 2, 3 is actually all the non-zero terms. So this thing is equal to cosine 3x. How do you find the radius of convergence? Ratio test on that. Where is it centered? 0. So this, what happens is cosine of 3x is some graph. So this series will start by approximating cosine 3x really well around 0. And then the more terms you add, the better and better it will approximate the function cosine 3x away from 0. And the more terms, the better it approximates farther and farther away from 0. Okay, any questions? Okay, so now we need to try the Taylor series. So now Taylor series is when you're centered about something other than 0. So we're going to try this one, centered about x equals 3. So this is what we're doing. Instead of the derivatives, the function and the derivatives taken at 0, now it's the functions and the derivatives taken at 3, centered at 3. Okay, but you still definitely still want to make the table, and I recommend keeping track of, instead of multiplying things out, like when they're squared, cubed, fourth, or when factorials start coming into it, keep everything in expanded form so that you can see the pattern. Okay, so keep everything in expanded form. Don't multiply.
I just wrote down this.
Okay, can we go right to this? Can you guys have consensus on this? F, the function evaluated 3 would be ln of 6, okay? Then, what is it? 1/3? 1 over 2x times 2 evaluated at 3, 1/3. Okay, second derivative. We better do it.
Negative
1 over 2x times 2. It's 1 over x. So it's negative x to the minus 2, right? So it's negative 1 over 3 squared. Agree? Then x to the minus, 2x to the minus 3. 2 over 3 cubed. Let's have consensus. I'm going fast. So negative 3 times 2 over x to the 4th, or x to the minus 4th. I'm going to do over in the fractions. So minus 3 times 2 over 3 to the 4th. This is what I mean by don't multiply things out, because look what's forming here. What's forming here on the top? Now it's going to be 4 times this, right? 4 times 3 times 2 over. Yeah, so as you see, the factorial is forming here. So it's going to be 4 times 3 times 2 over 3 to the 5th. And then negative 5 factorial over x to the 6th. Negative 5 factorial over 3 to the 6th. That's when n is what? 6? And then positive 6 factorial over x to the 7th. Follow. All right, here we go. Quick. So notice there's a pattern here, which is not anything to do with this first term. So we're going to set up the summation starting at n equals 1. Okay? And then have ln of 6 out here. So ln of 6 is by itself. It's not like any of these others. So we're just going to start by writing ln of 6 plus summation. And we're going to, don't know if we should or not. Should we start back at 0 again, or should we start at 1? We're going to flip it back to 0. Okay, so then this becomes 0. 1, 2, 3, 4, 5, 6. So it was 0, 1, 2, 3, 4, 5, 6 before. Now we're going to start our summation starting at n equals 0. So again, the easiest thing to do is look at these big ones, right? So when n equals 6, first of all, we've got the alternating effect, right? We've got alternating effect, so we've got negative 1 to the n. See if it works. Does that give us the right thing? When n is 0, it's positive. N is 1, negative. That's good. Then what do we have in the numerator? We have n factorial. over? Nope. 3. Oh, wait a sec. What am I trying to do here? I'm still doing this, right? All I'm doing so far is this. Okay, so that's going to be 3 to the n plus 1. So all of that is just these values here, which is the nth derivative at 3. So then we also need what? N factorial. That's this thing right here. Then times x minus 3. Not good. I shifted it. Shouldn't have done that. Is it n plus 1 now? Yeah. It's n plus 1 because I shifted back, right? I shifted the n back to 0, so then that would have to be n plus 1. That comes from the fact that we shifted back 1. Okay, and so then the n factorials go away. And we get and that's it. Question? Some other question over here.
Oh, when you made this chart, 0 starts at the second one and 1 at the first.
It's the ln of 6 that I taken over here. Ln of 6. Just adding that on separately because it's not part of the pattern. It's not part of the pattern of these. Get the ln of 6 plus, then I'm starting from here, and then equals 0 now, starting here. Better? Yeah. Yeah, we'll come up